Hi everyone. So today we'll be discussing on the topic maximum closure of the graph. And as I had said, so this is going to be the last algorithm on the advanced graph based algorithms playlist. Yep. So next we'll be moving on with dynamic graph based algorithms. So as I've said, this is going to be the last algorithm within the advanced graph based algorithms playlist. So let's see what the definition part says here. So mainly we'll be discussing on the topic maximum closure of a graph algorithm. Yep. So let's see. So maximum closure of a graph, what it does, it finds the subset of the vertices such that mainly what it does, it finds the subset of the vertices such that if a vertex is chosen, all its outgoing neighbors must also be chosen, right? So if the suppose if we are selecting certain this one vertex, or if you are choosing certain vertex, then all its outgoing neighbors must also be chosen. So that's what we have to keep in mind. Yep. So the total weight, right? Weight is nothing but the profit here. So the total weight of the selected vertices is maximized. Yeah, this is the important part. Yep. So what it does, the total weight, whatever the profit of the selected vertex is maximized, it is solved using the maximum flow or the min cut transformation. Either we can make use of the CAPS algorithm, or we can just go with this one Dinix algorithm, as we need to solve this one using the maximum flow or the min cut transformation. Yeah. Let's see the same actually. Let's see the same thing in the action. First thing, let's discuss the algorithm. Yeah. Let's discuss the algorithm by taking very simple example, and then we can just write the code. If everything goes well, if we get the desired output, then we can just discuss the complexities. These things we'll be doing. First, let's discuss the algorithmic part. Let's do that. So here, the first thing, see, let's move on with the approach part actually. 1 second, just give me a second here. Yeah, suppose we have three vertex actually. You can clearly see the node or the vertex here, A, B, as well as the C respectively, with the weight +5, +3, as well as -4 respectively. For the A, we have the weight +5. For the B, we have the weight +3, and for the C, we have the weight -4. Yeah. So this is the simple example that I have considered. So let's move on with the dependencies part. So I have shown you the graph here. See, A consists of +5 weight, B consists of +3 weight, and the C consists of -4 weight actually. How they are connected within the graph, I have shown you clearly. I insist you to pause the video and have a look into it. And this is the flow network transformation actually. Yeah. So A from the source actually, this is source. As we are dealing with the maximum flow, this is going to be the source, and this is going to be the sink. And from this one source to A, it would be 5. From source to B, it would be 3. And from A to this one C, actually, this one A to C and B to C, it would lead to infinity. And this one actually from C to sink, actually, it is going to be 4. See, uh, positive source node, negative node, as well as the sink. You can clearly see here. Dependence is nothing but indicates the infinite edges. So what are the dependencies here? First, we will be considering A to C, this part. Yeah, dependencies, this part. A to C, as well as we have B to C, this part. Yeah, A to C as well as the B to C. You can clearly see here. Meaning, if we take A or B, we must take C as well. They are completely dependent on this one. C is completely dependent on either A or either B. You can clearly look at the graph and you can say that. Yep. So C is completely dependent on A or B. So the dependent edges are A to B as well as B to C. It's as simple as that. Now, yep. Let's move on with the decision part actually. So taking A plus B gives 5 plus 3 minus 4, nothing but 4. Taking only A gives 5 minus 4, 1. See, taking A plus B gives this one. What do we call? 5 plus 3, because see, A we have this one 5 here, and B we have here 3. So taking A plus B would give 5 plus 3 minus 4. We have -4 for this one actually. C to sync actually. We have to consider C if we consider A or B, right? Taking A plus B gives 5 plus 3 minus 4, nothing but 7 minus 4. So, sorry, 8 minus 4, that would give 4. And taking only A would give, if we consider only A value is +5, +5 minus 4, which would lead to 1. Taking B, so B value is 3, 3 minus 4, again, it would lead to -1 this time. Yeah. Instead of the +1, it would lead to -1. So taking none would lead to 0. If we are not considering any vertex, then it would lead to 0. So it would be best if we take A, B, C. So profit would lead to 4, this one. If we consider A plus B, both actually, both are dependent. C, if we are considering C, either we have to consider A, B, or A plus B. These three things we have. So profit, which one gives the more profit here. Taking A plus B gives us the more profit here, right? So taking A plus B gives us the more profit. So let's consider the same thing here. 5 plus 3 minus 4, which would lead to 4. Yeah, profit would be 4 here. So the output has to be, if we consider this input within the code as well, let's consider the same input actually. Yeah. So if we consider this one as the input, so the output that we need to get here is A, B, and C respectively. Yep. So this is fine, I believe. So this is it for the algorithm actually. This is it for the algo. It's as simple as that. So I insist you to do one thing. Just pause the video and have a look into it. By looking at the graph itself, you can scan the whole algorithm if you know the algorithm, if you have understood it. Yep. So it's very simple one. Yep. Now let's do one thing. As we have discussed the approach part, we have already discussed the definition part as well as the approach part. It's we are good to write the code actually. Let's try to articulate the same thing in the form of code. Whatever we have discussed till now, let's try to articulate the same thing in the form of code. Let's do that. So let's move on with the same here, right? So first thing, we'll be making use of the buffer reader as well as the print writer, and also we'll be making use of this thing, what we call different utilities. So let me import io.star, yeah, input output package as well as the utility package. Yep. So this is fine. So let's move on with the further things. Now, within the main class actually, what we'll be doing first thing. So let's go with the edge structure. Basically, we'll be making use of the edge structure for the residual graph. So I'll just go with static here class. So let me go with edge. So this is fine. Within the edge class, first thing, what am I going to do? So I'll just consider we need two, as we are going with the, as we'll be going with the, this one. What do we call? Dinix algorithm. So I need two, as well as I need from I don't need, I believe. I just need the capacity, and also I need the this one. For the reverse edge, I'll just consider REV. Yep. So this is fine. Yep. Let's move on with the constructor part. So let's this one initialize certain things. So I'll just go with the edge here. I need same thing actually. Let me consider. For the 2, I'll just consider T. For the capacity, I'll just consider C. And for the rev or the reverse, I'll consider R. So I'll just go with 2 equals T and capacity. So why, what happened to this one? Correct itself, right? Method return type missing or constructor name does not match the class name. What I have given here, edge itself, right? Oh, I have closed the this one here. Let me remove this one. 1 second. I have one more this one here. So let me format the code so that the code looks good. Now if I give yeah, now it has to show capacity. Let me assign this one to C, and the final one is nothing but the reverse. Let me assign this one to R. Yeah. So this is fine. I'll just come out of this one entirely. Now we need the adjacency list of graph. For the adjacency list of graph, I'll just go with the static. So let me go with the list. Within the this one, I'll just go with the edge. Yep. So this is fine. Finally, let me make use of the variable graph. Yeah. So this is fine. Next, we need the method to add the edge in the residual graph. We should be able to add the edge in the residual graph, or the graph that we have that we'll be considering, right? So for that, I'll just go with a static here. So this one will be void add edge. So this is fine. I need same 3 parameters here, int u, v, yep, as well as this one capacity. I'll just go with a yeah. So within this particular method, so as we are dealing with the this one undirected graph, we have to go with the reverse edge as well. Yep. So I'll just write it in this way. What happened here? Oh, did I close this one over here? Yep. Let me close this parenthesis here. Yep. So this is fine. Within this particular method, first let's add the forward edge as well as the reverse edge. Let's do that. So I'll just go with a graph here, graph of u dot add. Let me go with the new edge here, this one. So what are the things that we need to add? V, capacity, and graph of V. First, I'll just go with a V, then capacity, then let me go with graph of V, graph of V dot size, actually size of the graph. Yep. So this is fine. This is, we have successfully added the forward edge. Now we have to add the reverse edge as well, right? So graph of V dot add new edge. So this one will be u. This is correct actually. Let me write this one u. Instead capacity, I'll just give 0. As we are adding the reverse edge, we have to go with a 0. And this one will be, instead of graph of u, I'll just go graph of v, I'll just go with a graph of u dot size here. After size, I'll just go with a -1. Yeah, -1. So reverse edge will be having the capacity 0 initially. Just keep this in mind. That is the reason here I have initialized the capacity with 0 rather than the capacity itself. Yeah, variable. So next, let's move on with the further things. Yeah. So the first thing is I'll just go with the level as well as the pointer. Level because we have to store the level graph, nothing but the distance from the source, and pointer because we need the pointer to track used edges in the DFS. So we will be making use of the DFS as well as the BFS, as we'll be going with the DINIC. Yep. So let me initialize two things. I'll just go with the static here, int. I'll just go with the level. So this is fine. And let me go with the static here, int, and let me go with the pointer. Yep, so this is fine. Next, let's go with the BFS. BFS basically what it does, it builds the level graph. Yeah, so first we are going with the DINIC algorithm. We need BFS as well as the DFS both. So let me go with the BFS first. So I'll just go with the Boolean. So this is fine. Let me go with BFS. I just need two parameters. One is S and another one is T. Yeah, so within this method, initially I'll just fill this one with a fill the level with -1. Yep. So we are just marking all the nodes as unvisited by filling this one level with a -1. The second thing is with BFS uses queue. We know that. Yeah. So we have to make use of the queue here. Queue of instead of the edge, let me give integer, as we are dealing with the integer. This will be of the type integer. The variable, I'll just keep the same thing. Linked list, I just make use of the linked list everywhere. So let me change this one to the array queue. Linked list also works. No worries, right? So this is fine. So next, let's start from the source. For that, I'll just go with the add of the S. Yep. So we have considered variable S. For the source, I'll just add S. Finally, the level of the source, let's set the level of the source to 0 initially. So I'll just go with, instead of -1, let me set this one to 0. So next, the pure BFS part, let's move on with a standardized BFS while loop actually. While not of q dot is empty, q shouldn't be empty. In that case, first we have to go with the current node, or we have to remove that, right? So I'll just go with the int q equals q dot poll. So this is fine. The next part would be nothing but we have to traverse all the edges. For that, I'll just go with a for loop here for edge. So this is fine. E of, so let me go with graph of u. Yep. So this is also fine. So within this particular for loop, first thing, so let's go with a valid edge and unvisited. So I'll just go with if here e dot capacity. Yep. If it is greater than 0, and so let me go with the level of this one, e dot 2. Yep, level of e dot 2. So this is fine. So if it is equivalent to -1, then in that case, what we are going to do actually within the if condition. So we have to assign the level and we have to push into the queue. For assigning this one level, I'll just go with level of e dot 2. Let me assign this one to this one vertex u actually, not e dot capacity. So this one will be level of u plus 1, which is absolutely correct. Next, we have to push into the queue. For pushing or adding that one to the queue, just go with q dot add e dot 2, which is absolutely correct. Let me format the code. So the BFS part is almost complete. We are left with only one thing. We have to return Boolean value true if the sync is completely reachable, right? So I'll just go with we have here, right? So this one I have to consider. So let me return the sync is reachable. Yeah, I have shown you the graph already while we had discussed on the approach or the algorithm part. Source and the sink I had shown you within the graph. Yeah. So if you would have looked into it, you would have understood this one easily. So if you don't know the DNX algorithm, so if you want to go in detail, actually, if you want to learn the DNX algorithm, let me tell you one thing. The DNX algorithm is present in this one, 150 algorithms playlist. So it is present in Java. So we had discussed that one in the Java as well as we have discussed on the, we had discussed using Python programming language as well. Yep, you can just look into the video and you can just come here, right? So let me come out of this one entirely. Now we are done with this part. Level of, so this one, so this one, instead of just true, what we have to do, I'll just we have to this one return true if sync is reachable, right? So I have to go with the level of t actually. Yeah, we have to check whether it is not equivalent to -1, then only it is set to true. So we have to write in this way. Sorry. Yeah, let me format the code now. Now we are done with the DFS. So Linux also uses this one DFS along with the BFS, right? So let's go with the DFS. DFS basically what it does in the Linux, it sends the flow using the level graph. So I'll just go with static again. So I'll just go with int DFS. So let me go with U, let me go with T, as well as let me go with the flow. Yep. So this is fine. Within the DFS method, the first thing, if suppose U equals T, or I'll just go with flow, if it is equal to 0, then in that case, we have to return flow. Yeah, we have to return flow. So this is the base case actually. Yep. Next, let's move on with the iterating the edges. We have to iterate edges. So I'll just make use of the for loop here. So this one, uh, we have already made use of the pointer variable. So I'll just check pointer of U. If it is less than graph of U dot size, which is correct, then pointer of U plus plus. We are iterating edges actually. Yeah. So within this particular for loop, the first thing I'm going to do is, so I'll just consider edge here. So where we have already written the class edge actually. I'll just consider variable E. Let me assign this one to graph of U dot get pointer of U, right? So this is correct, which is absolutely correct actually. Next, let's write the simple if condition here. So because we have to check for the valid level edge and send the flow, these two things we have to do mainly. For that, I'll just write the simple if condition. I'll just go with E dot capacity here. So if it is greater than 0 and level, this one, E dot 2 actually, if it is equivalent to not -1, if it is equivalent to level of U plus 1. So yeah, level of U plus 1. In that case, within the if condition, what we'll be doing? So we will reduce the forward capacity, will increase the reverse capacity, and we will return the pushed flow. These three things will be doing, right? When before these three things, we have to send the flow as well. Before doing these three things, we have to send the flow. For sending the flow, I'll just make use of the keyword pushed here. So let me make use of keyword pushed. So this one will be, let's recurse now. I'll just go with the DFS of E.2 T, as well as for the just flow, we have to consider the minimum value. So I'll just go with, sorry, I'll just go with math.mun of flow, as well as I'll just go with the E.capacity. Yep, so this is fine. So after successfully sending the flow, let's write the simple if condition now again. Yeah, nested if. So I'll just go with a pushed here. Suppose if pushed is greater than 0, then in that case, first let's reduce the forward capacity. For reducing the forward capacity, I'll just go with the E dot capacity equals E dot capacity minus pushed actually. This one. Yeah, it's as simple as that. Now we have to increase reverse capacity. So I'll just go with graph of E dot 2 dot get. So I'll just go with graph of E dot 2. So let me go with get here. So I'll just go with E dot REV. Yeah. So this is fine. Dot capacity. Yeah. So I'll just go with the same thing plus flow. Yeah. It's as simple as that. So we don't have to go with the flow. We have to go with the pushed actually. The variable we have considered as pushed, not the flow. We shouldn't go with the flow. Yep. As we are just increasing the reverse capacity, we just have to go with the pushed, not the flow. Finally, we have to return the pushed flow. Pushed flow, we have considered the variable pushed, right? So I'll just return pushed here. It's as simple as that. Now we are done with this part as well. Almost we are done with this part. The only thing that is left is nothing but if no flow is pushed, in that case, we have to return some value. So either we can go with the -1. As we are dealing with the integer, it's better to go with a 0. Yeah. In that case, I'll just return 0. Yep. So this is fine. Let me come out of this one entirely. Now, if you know the Linux algorithm, it consists of the BFS as well as the DFS. Both we have written. Both the methods we have already written. Now we have to implement that one in the max flow method. Yeah, let's do that. I'll just go with static. So let me go with int. So I'll just go with a max flow here. So let me go with S, as well as let me go with T. Yep. So this is fine. Within the max flow method, we'll be making use of BFS and DFS both. First, let me this one initialize the flow to 0. So next, so while we have the path, in that case, we have to reset the pointers, right? So I'll just go with while. Let me go with the, or let me call the BFS method that we have already written with the parameters S and T respectively. Now within the while loop, the first thing we have to reset the pointers. So I'll just go with arrays.fill. Yeah, arrays.fill of, let me go with the pointer as well as the 0. Yeah. So we have successfully reset the pointers. Next, let's do one thing. I'll just go with a variable pushed. Yeah. Let me go with a variable pushed. So this is fine. Um, so let me go with a while loop as well. So I'll just go with a while here. So I'll just go with pushed. Yep. Pushed equals DFS of this one. Let me give mention all the parameters here. ST. So I'll just go with integer dot max value, this part. So this is also fine. Integer dot max value. Let's check whether it is greater than 0 or not. So within the while condition, we have to add to the total. So we just have to go with a flow equals flow plus pushed actually. So this is absolutely correct. So let's do one thing. Finally, all we have to do is we have to return the maximum flow. So let me return max flow. Max flow, for that, for the flow, we have considered the variable flow itself, right? So let me return this one. Right? This is it for the algorithm. Yeah, this is it for the algorithm actually. Yeah. So we just went with a BFS. Initially, this one added, as we are dealing with this one, what do we call? Undirected graph actually. We went with a forward edge as well as the reverse edge, and then the global variables. Then we went with the BFS, DFS as well as the max flow. Within the max flow, we have implemented this one BFS as well as the DFS. This is pure Linux algorithm. So this is it for the main this thing actually, maximum closure graph, right? So this is fine. Then now we are left with only main method. We have to consider example. Usually I take the example from the Google, right? So let me do that. Just give me a second here. So let me do one thing. I'll just paste it over here, the main method. Yeah. So first thing, what we are doing here. So this is buffer data and the print data, which is completely related to the input output part. Yeah. So that is the reason we have uh, made use of the input output package. I have imported the input output package at the beginning. So next, so we have considered n equals 3. So if you remember the graph, the same example that I had shown you while discussing the this one algorithm actually, the same graph we are considering here, the same example. N equals 3. If you remember, we had nodes A, B, and C with plus 5, plus 3 as well as one more value I forgot actually. I considered, I don't know, maybe we went with this one 2 or something. I don't know exactly, but with this one, n equals 3, right? So here, a source we have set to 0 and sink we have set to n plus 1. Source node and sink we have to consider at any cost, right? So as we are making use of the max flow. Next, here graph equals this one. This is nothing but we are initializing the graph with a extra node. So this is fine. Next, we are going with the level as well as the pointer. Level and pointer is nothing but the level array as well as the pointer array, right? So we also need weight for individual this one, what do we call vertex actually, we need the weight. So weight is nothing but here this one, weights of the nodes actually. This is one based indexing. Don't forget this one. We are going with a one based indexing here. So total positive is nothing but the sum of positive weights. Yeah, sum of positive weights. Then this for loop until here actually, what we are doing here. So we are building the graph based on the weights. So based on the weights, what we are doing, we are building the graph, right? So next, what we will be doing. So here, after this, after we have successfully built the graph based on the weights, we are just adding the dependency edges. So this one, adding the dependency adjustments, this one. Yep. So add edge, we have already written method. As we are dealing with this one undirected graph, we have to go with a reverse edge as well here. So we are just adding the dependency edges, nothing but with the infinite capacity. That is the reason here we have went with a positive this one infinity initially. A to C and B to C. In the flow graph, I had shown you that from A to C, we had mentioned infinity, and from B to C, we had mentioned infinity. So we have considered the same value here, right? So 1 to 3, 2 to 3. So this one edges actually. I had shown you this one graph, maximum flow graph, or this one flow graph, while discussing this one approach part actually, or the algorithm part. If you don't know, if you are not able to remember currently, you can just go to the if you can go you can just go to that part of the video, and you can just this one look at the graph, and you can just come back here, right? So finally, this one is nothing but we are computing the max flow. We have to compute the max flow itself, right? So the result is nothing but here maximum closure value, right? So this is nothing but the maximum closure value. We are this one, we are trying to find the maximum closure of the graph itself. So the result variable, what it does, it finds the maximum closure value. Finally, we are printing the result. After successfully running the code, we have to get the output immediately. So I'm making use of the flush. As we are going with the print writer, you can just make use of the close as well. Either of them works, flush or close. Yep. So this is it for the coding part. So now we have successfully written the algorithm. So one more thing, you can make use of the curbs algorithm as well for this. It works with the curbs as well, right? Curbs for the maximum flow. Yep. So either of the algorithm works. You can just go with this one, Dinix or the curbs. So Dinix is what I prefer, right? So let me run the code now. So you can clearly see we are getting the output 4. If you remember this one, during the approach, we considered the same example. We got the profit 4 actually. Yeah, we are getting the desired output 4, which is absolutely correct actually. We got 4 and if we consider only A had +5 and we got -4, that is 1. A value was 1. B value was 3 minus 4, it was -1 and 0 if we don't consider anything. So out of A plus B, A as well as the B, and when we do not consider anything, we got 0, this one 4, as well as this one 4, 1, -1 as well as the 0, which is the maximum when we considered A plus B. So the profit was 4. We have to get the output. So we have written the code in such a way that we are displaying the profit actually, not the edges, which not the vertex that would lead to this one, the maximum profit, right? So we are showing 4 in the output. We have written the code in such a way that we have to get the maximum profit. So we are getting the desired output here, right? We can just check that part of the video where we had discussed this one, the algorithm, by considering the same example. We are getting the correct output. Yep. Now we are done with this part. We are left with only one thing, nothing but discussing the complexities for the code that we have written. Just give me a second here. Did I leave anything? No, right? Mm, yeah, this is fine. Let's do one thing. Let's quickly discuss the this one, complexities actually. Yeah, so this is fine. So what would be the time complexity here? The time complexity would lead to because of, for the edge we have went with E, and this one will be this one E, nothing but the edge, into square root of V, into square root of V. So this is going to be the overall time complexity. Yeah. So the time complexity would lead to because of E into square root of V, right? So as we are going with the Dinic average, it can be almost equivalent to because of E, V actually. We can just write it on this way as well. Yeah, it's almost equivalent to this one because of EB, right? So what would be the space complexity here? You would have already guessed actually. So this would lead to big of V plus E. It is completely dependent on the memory, is completely dependent on the number of vertices as well as the edges. Yeah. So this is nothing but graph plus residual edges. Vertex as well as the edges, or graph plus residual edges. Yep. So this is going to be the space complexity. The time complexity and the space complexity for the code or the algo that we have written would lead to big of E into square root of V and big of V plus E respectively, right? So this is it for the algorithm part. This is it for the algorithm part. So let me delete this one second. Yeah. So now we are done with the maximum closure of a graph algorithm. Let's do one thing now. Let's try to this one, implement the same thing in one of the problems. So we can just get to know the algorithm even better. How can we implement the same thing when solving certain problem, right? So I'll just take one problem and let's try to implement the same, yeah, the same algorithm actually. Yeah, let's do that. So let's move on with the this one problem part actually. So this is one of the best problems that I have seen to implement the max closure of the graph. Yeah, let's do that. Let's try to understand the question. Yeah, so I can just go through the question. So this is 311E. Yeah, Codeforces 311E. So I can just go through the question. It's easier to understand. I'll just summarize the question so that it will be easier for us to solve the problem entirely. Yep. So you can just go through the question. Let me summarize the question now. Just give me a second here. Yeah. So first thing, we have n docs. Accordingly with the question, we have n docs. Yeah, it's simple. We have n docs. Each can optionally change the gender at cost. This cost v of I. Each dog can change the gender at the cost v of I. Yeah, at the cost v of I. Just remember this. Yep. So there are m people. Yeah, there are n dogs. Each dog can change the this one gender at the cost v of I, and there are m people. Yeah, there are m people. Each gives reward w of I. Each this one. Yeah, each person gives the reward w of I if a subset of dogs matches a required gender, right? If the subset of the dogs matches a required gender, then each person gives the reward w of I. Just remember this. It's very important. If a friend is not satisfied, suppose if a friend, I'll just write here f, if the friend is unsatisfied or not satisfied, then we must pay penalty G. Yeah, then we have to pay the penalty G. Yeah, this is very important. Yep. If a friend is not satisfied, we must pay the penalty G. So what is our main goal here? This is the question. Yeah, I hope this is clear. Let me read this one again. Just listen to this carefully. This is very important. Yeah. So we have n dogs which can each can optionally change gender at the cost v of I. Yep. So this is fine. So there are m people. Each gives reward w of I if a subset of the dog matches the required gender. It's very simple to understand. Yeah. So this is fine until here. Next one, if a friend is not satisfied, in that case, we must pay the penalty G. If the friend is not satisfied or unsatisfied, in that case, we must pay the penalty G. Right. So what is the main goal here? The main goal is to maximize the profit. Yeah. So I'll just give here maximum profit is equivalent to rewards. Yeah. Maximum profit is equivalent to rewards minus costs minus penalties. Yep. So this is it for the maximum penalty actually. Yeah. Again, what is our main goal? Our goal is to maximize the profit. So to maximize the profit itself, we'll be making use of the maximum closure of the graph actually. Mainly profit in the sense we have already seen the algorithm actually. Yeah, within the algorithm we had considered the maximum value itself, maximum profit we got for. Yeah, so to maximize the profit itself, usually we consider the maximum this one closure of the algorithm. Yeah, maximum closure of the graph algorithm mainly. Sorry. Yeah, so mainly here one more thing, the to maximize the profit, this one the formula is nothing but maximum P, uh, nothing but maximize profit. Maximize profit is equivalent to rewards minus costs minus penalties. Yep, minus penalties. Yep. So this is the formula that we have to remember. So this is it for the question. All we have to do is we have to maximize the profit. And one more thing, if the friend is not satisfied, and then we must pay the penalty G. That also we have to remember. So this is the question. It's as simple as that. Yep, it's as simple as that. Let me delete this one. So this is fine. One more thing, we have been given this one. What do we call constraints here? Input and output. You can just go through that. So here n we have been given greater than or equal to 1 and less than or equal to 10 to the power of 4. And m we have been given greater than or equal to 0 and less than or equal to 2000. And g we have been given greater than or equal to 0, less than or equal to 10 to the power of 4. So that's what they have given. So we have to go through this one once. So yeah, just go through this one. And the third line contains n integers here, v1 to vn, and v has to be greater than or equal to 0 and less than or equal to 10 to the power of 4. That's what they have mentioned here, right? So just go through this one. They have given for w as well as k as well. See this one. Yeah, for the weight as well as the k also they have given the same thing actually. You can just go through the constraints, and in the output part they have strictly mentioned here, print a single integer, the maximum money small r can gain. They have strictly mentioned. And note that the integer is negative if smaller will lose money. Suppose in that case, if you have to pay the penalty, in that case, note that the integer is negative if the smaller will lose money. Yep, they have strictly mentioned here. Yep. So this is fine. Yep. So this is it for the question. Now let's do one thing. We are done with the question. I hope the question part is completely clear. Next, let's do one thing. Let's discuss the approach. Yeah. So anyhow, we know that we'll be implementing the maximum closure of a graph algorithm. Yeah. So let's discuss the, what do we call, approach. Then we can just write the code accordingly with what we had discussed. The same thing. Let's articulate the same thing in the form of code. If everything goes well, if we get the desired output, then we can just this one move on with the complexities point. These things we'll be doing. First, let's keep all other things aside and let's discuss the approach. Yeah, accordingly with the question, let's discuss the approach. One second. So let's move on with the this one approach part. See, input I have considered the same thing here. Actually, you can clearly see 0 followed by 1110, this one, and 18623. Yeah. So this one docs we have 0 1110 and cost we have 18623 and G we have been given 9 in the input. You can clearly look at it. The first line actually 5 followed by the 9. So basically what we'll be doing, as I've said, we'll be modeling this max closure problem using the flow. Yep. We have to go with the flow. We have to consider the flow itself, right? So for the max, this one closure, either we can just go with a cup or we can just go with a Dinic. So let's go with a Dinic. So let's see that one later. Next, first, actually, let's this one move on with the further things here, right? So what is the key idea? So we have to decide. So for each dog, whether to flip or not. Yeah, we have to decide for each dog we have to flip the gender or not. Yeah, so that one we have to decide, and for each person whether to satisfy them or not. Yep, so these two things we have to decide. Again, what we have to do, for each dog we have to decide whether to flip the gender or not, and for each person whether to satisfy that condition, whether we have flipped or not, that one we have to satisfy them or not. For each person, that also we have to decide. These two things actually we have to do. That's the key idea mainly. Yeah, so let's go with a node. So what's the node here? The meaning of the node. See, nodes 1 to n is nothing but the docs. Just remember this one while writing the code. It is necessary actually. This part I wanted to show you. This one, nodes 1 to n, whatever we represent, that is nothing but the docs, and nodes n plus 1 to n plus m, that is nothing but the people. Yeah, don't get confused in the future, right? So nodes 1 to n docs, nodes n plus 1 to n plus m, nothing but the people. Yep, it's as simple as that. Now, S is nothing but the source and T is nothing but the sink. Again, S is nothing but the source, T is nothing but the sink. Now let's move on with the modeling rules. Modeling rules, first one, let's go with the dog flipping. So the key idea we have only two. So see here, I have already this one shown you. So we have to decide whether to flip or not. And for each person, we have to decide whether to satisfy them or not. These two things. First, let's go with the dog flipping. Yeah, let's go with a dog flipping here. So if we flip the dog I in the sense iteration, the number of, based on the number of dogs, the first dog. Yeah, if we flip the dog I, we have to pay the cost v of I. So in the question, for each gender, this one flip, actually we have to pay the cost v of I, right? If we flip dog I, so we have to pay the cost v of I here, which is modeled as either we have to keep original one or we have to flip nothing but the by paying the cost. Actually we have to pay certain cost to this one, flip the gender of the dog. See, again, within the dog flipping, if we flip the dog I, then we have to pay the cost b of I. This is modeled as either we can keep the original or we can flip, nothing but the cost here, right? So second one is nothing but the person satisfaction, this part. So key idea, within the key idea we had discussed the same thing. This part is done now. Yeah, this part is done. We do not have to worry about this. Now for each person, so we have to decide whether to satisfy them or not. Yeah, we have to this one, decide whether to satisfy them or not. So how we will be able to see that? See, for the first one, so each person gives profit w, right? Each person gives the profit w because we have to pay the cost b of I actually, right? Based on, for the each dog, if we are flipping the gender, we have to pay the person has to play the person has to pay the this one profit w, the cost v of I. So so we get the profit w actually, or if not, then we have to pay the penalty g. So this one I have we had discussed during the question part actually, or else we have to pay the penalty g, right? If friend and not satisfied, in that case we have to pay the penalty g, right? Next, let's move on with the dependency part. Now we have discussed both the idea actually, key ideas, right? Two things, flipping the dog and whether the person is satisfied or not, right? Based on the flipping of the dog. So those two things we have said, this one we have discussed. Now let's move on with the third one, nothing but the dependency. Dependency, this part is very important actually. See, suppose for example, person wants dogs suppose 3, 2, 1 to be gender O, right? So this is one gender, 0 and 1 let's consider here, or O and X if you are considering. Suppose if the person wants the dog 3, 2, 1 to be the gender O, means if we take this particular person, all the dogs must match. Yeah, if we take the person that if we are considering that particular person, then all the dogs must match actually, means they have to be of the same gender, right? So to be uh, it has to be gender O actually, right? So this is fine. This is encoded using dog to person, nothing but infinite capacity. With the infinite capacity, we will be seeing that one when we write the code. You just have to understand that we will be encoding using dog to person with the infinite capacity. Yeah, just remember this. Now let's move on with the graph representation. Let's go with a graph representation here. So this is the more detailed version, right? So here S2 dogs we have, S2 person, then this is nothing but the T actually. Yeah, don't get confused. This is nothing but the D. So S2 dog 1. Suppose if we are having number of dogs here, 3 to 1 we have considered here, right? 3 to 1 accordingly with the input. Suppose if we are considering 3 to 1 actually. So S2 dog 1, person 1, T. S2 dog 2, again same thing to the person T. S2 dog 3, again the same thing to the person T. So this is the more detailed representation. That's it. So dependency is nothing but dog 3, dog 2, dog 1, all are dependent on the person 1. Yep. So all the dogs, dog 3, this one, basically dog 3, dog 2, dog 1, all are dependent on the same person as per the example that we have considered, because this particular person wants the dogs 3 to 1 to be the gender O. So all the dogs, dog 3, dog 2, as well as the dog 1 is dependent on the person 1, meaning if the person 1 is chosen, then all dogs must satisfy that particular condition. Yeah. Suppose if the person 1 is chosen, then all the dogs must satisfy the condition. Now let's move on with the next step by step explanation. So let's discuss how we can derive to the output accordingly with the input that we have considered. So our main goal is to maximize the profit, right? So main what they have asked in the question, we have to maximize the profit, and we have discussed about the formula to maximize the profit. That also we have discussed already. Yeah. So our main goal is to maximize the profit. So first step here would be, so first we have to try satisfying the people. First, let's try satisfying the people. So we'll check the combinations here. So suppose first let's go with the first person. First person needs dogs 3 to 1, right? 3 to 1 to be this gender actually, O, gender O, right? So first person needs dogs 3 to 1 to be the gender O. Some dogs are already 1, so we need flipping. Accordingly with the input they have given here, you can clearly see some dogs are this one already 1, 0, 11110 we have considered here, right? So this is the first input. Yeah. So this one we are considering 0, 11110, and here some dogs are already 1, so flipping is necessary here, right? So we have to flip that one to the 0. 3 to 1 we are considering. Person 1 needs the dogs 3 to 1 to be O, or this one O actually. Yeah. Some O, not O, sorry, 0. Yeah. O or 0. Usually we go with the 0x for the question. In this case we are going with the 0 and 1 actually. Yeah. Some this one person 1 needs dogs 3 to 1 to be 0. Some dogs are already 1, so this one, those dogs who are already 1 needs flipping to 0. Yeah. So the cost is involved here in this case. Yeah, the cost is involved. And let's move on with the second step. So we will evaluate the trade-off. So for evaluating the trade-off, see, for each person profit, we are calculating this one by this. Yeah. W minus cost to make the dogs match. Yeah. So this is underscore W minus cost to make the dogs match. So we'll be going with this particular formula for calculating the profit actually. Yeah. Again, profit is equivalent to W minus cost to make the this one dogs match actually. As certain dogs are already 1, it needs flipping for the person 1, right? So to satisfy the person 1, dogs has to be flipped from 1 to 0. Yeah. So next, let's move on with the step 3. So let's consider the friend penalty. Yeah, let's consider the friend penalty. If the friend is not satisfied, then we have to pay the penalty of G. Yeah, if the friend is not satisfied, in that case we have to pay the penalty G. Yeah, that's what they have strictly mentioned in the question, right? So we are considering the friend penalty here. If the friend is not satisfied, in that case, what we lose actually, or we have to pay the penalty G, or we will lose G. Lose will be equivalent to the G. So this is fine. Now let's move on with the last step or the final step. So flow decides the optimal set actually. As we will be going with the flow, so we'll be going with the Dinix algo for the maximum closure of the graph. So basically flow decides the optimal set. So we will be going with the minimum cut, right? So we'll be deciding, we'll be finding the minimum cut. So what will minimum cut do? Minimum cut will pick the profitable persons, right? So what are the persons who, so yeah, who are the people who gives the profit actually? Minimum cut will pick the profitable persons, flip only required docs. Yeah, flip only required docs and avoid the bad choices. Yeah, if the profit, if we cannot gain the profit actually, in that case that will be avoided. Yeah, so what will the minimum cut do? It will pick the profitable persons, it will flip only the required docs, and it will avoid the bad choices. These three things. Yeah, the first step would be it would pick the profitable persons. Yeah, only the persons who gives the profit, then, or who gets the profit, or who gives the profit actually. Flip only the required docs, then avoid the bad choices. Then avoid the bad choices. Yeah, so this is fine. We have to get the profit, right? So overall final result would lead to 2 actually. Here in this case, overall final result would lead to 2. So this is it for the basically this is it for the this one approach part actually, how we will be approaching the this particular problem, right? So we'll be going with the max flow actually. For calculating the max flow, we have to know the Linux algorithm. We'll be making use of the BFS and DFS, and we'll be going with the finally we'll be what do we call, we'll be calculating the two things. If you remember the algorithm, yeah, at the end we will be calculating the maximum closure actually of the graph. Yep. As we are done with the approach, we have understood the question. We are done with the approach part as well. We are left with two things. One is writing the code. If everything goes well and if we get the desired output, or if we get AC, then we can just move on with the discussing the complexities for the code that we have written. Yeah, we can do that. For now, let's discuss the, or let's start writing the code. Yep, let's do that. Yeah, let's do one thing. Let's continue this one, writing the code. Just give me a second. Let me open the IntelliJ IDEA. So let me close this one. We have already discussed the algorithm. So let me open this one. Yeah, let's start writing the code. So the first thing here, so we'll be making use of the input output package, nothing but a buffer data and the print writer. So I'll just go with this one. We'll be making use of the different utilities as well. First, I have imported the utility package. So next, let me import the input output package as well. Yep. So this is fine. Next, what we'll be doing. So after importing the necessary things, then first we have to go with the adjacency list representation as we are dealing with the graph. So we have to go with the adjacency list representation. So I'll just go with the static here, int. So as we have the idea on the this one algorithm, implementation of this particular algorithm will be easy, not that much difficult. Yeah. So Dynamic actually we have implemented several times by now. Yeah, we have implemented the Linux algorithms several times, and we have to be good at it. Yeah, at this point of time, if you're following along with me. Yeah. So now I'll just go with the capacity. So this is fine. Let me go with the next, and also I'll just go with the head. Next, what I'll do, I'll just let's go with the distance, nothing but the height array for the that, right? So I'll just go with static here. Let me go with int. Yep. So I'll just go with distance as well as the gap. The next one, so let me go with the edge counter. For the edge counter, let me go with the static here, int. So I'll just go with the top. I'll just go with the S. Let me go with the T, and also let me go with the N. So the next, we have to store the final answer. For that, I'll just make use of this one, what we call answer variable or the result variable. Let me assign this one to the value 0. Finally, so I'll just consider here one large value. So I'll just go with a final int. So infinity value, I'll just consider not int. Infinity, I'll just consider 10 to the power of 9. 10 followed by 9 zeros. Sorry. Yep. 6, 9. So this is fine. We are done with this part. Next, all we have to do is we have to initialize the graph arrays. For initializing the graph arrays, I'll just go with static void. So let me go with int. Yep. So let me go with the int. Not int actually, init. We are going with the initialization part. So I need two parameters. One is maximum nodes and another one is maximum edges. You would have already guess this one. Yeah, within this initialization method, actually, let's initialize certain things. 2, I'll just go with new int of max edges. Yeah, so let me give you a max edges. So let me copy paste the same thing several times. I'll just go with, we need capacity, we need next, we need head, we need distance, we need gap, and we need top. Yep. So this one, I'll change this one to the capacity. So I'll just copy this one. Let me change this one to CAP here. And for everything, we'll be going with a new int of max nodes itself, except 2 actually at the end. So again, sorry, this is not 2 actually, this is top. So top, let's set this one to the -1. Yeah, initially let's set this one to the -1. Now after capacity, we need next actually. So let me copy this next. Let me paste it over here. Next we have head. Head, let me copy this one, this variable. I'll paste it over here. After head, we have distance as well as the gap. For the distance, I'll just copy this one. Let me paste it over here. For the gap, I'll just copy this one and let me paste it over here. Right. So we are done with this one. What happened? Oh, what happened here? So this one, I think I changed this one too. I copied the same thing here. Let me go with a gap here, right? So now the error will be gone. Yep. So I'll just come out of this one entirely. So we are done with the initialization, but I'll just come out of this one entirely. Now we have to add the directed edges, edge actually from U to V, right? So this is simple. So I'll just go with static. So let me go with void. So let me go with add edge or add, doesn't matter. I'll just go with the add here. So here, let me go with the edge U. Let me go with the edge V. And one more thing, we need weight as well. For the weight, I'll just go with the W, right? So this is fine. Within this particular method, so first thing, I'll increment the top as we are adding the edges. I'll increment the top. I'll just go with 2 of top. Let me assign this one to V and capacity of the top. So let me assign this one to the W. And next, I'll just go with the next of top here. So let me assign this one to the head of U. Yeah, let me assign this one to the head of U. And finally, I'll just assign the head of U to the top actually. Yep. So let me format the code so that the code looks good. Now let me come out of this one entirely. Let's add the forward as well as the reverse edge. So we are dealing with the undirected graph. We have to add the reverse edge as well. Let's add both actually. For this method, I'll just go with a add edge actually, named add edge. So I'll just go with add edge here. So I need again the same parameters actually, int uv as well as the w, edge u and v, and with the weight w. So the first thing, so I'll just go with here add. So let me 1 second, uvw. So this is fine. So let me change this one, or let me make this one to capital E. Yeah. So I'll just come here. Let me paste the same thing. So for the reverse edge, we have to change the capacity to 0. We know this one, right? So this one will be V and this one will be U, and the weight initially weight of the capacity will set this one to the 0. Yep. So this is fine. We are done with this part. I'll just come out of this one entirely, this particular method. Next, we have to implicate C. Suppose if P is chosen, then Q must be chosen as well. Yep. Suppose if P is chosen, person is chosen, then Q must be chosen as well, accordingly with what we had discussed. So this will be static void. So I'll just go with implies here. So I need 2 parameters. One is P and another one is Q. Right. So I'll just go with int P, int Q. So within this particular method, implies method, so Q and P, we have to add Q and P with an infinite capacity. Right. So I'll just go with add of Q as well as P with the infinite capacity. So I'll just go with a INF here. We have already added that one. We have considered that one in while declaring the global variables, right? Infinity to 10 to the power of 9. So I'll just go with one more thing, add PQ as well as 0. So I'll just go with P here. Let me go with Q and then let me give 0 here. Right. So this is fine. We are done with this particular method as well. So now we have to set the values of node I. J equals 0 means we are connecting with the sink. J equals 1 means we are connecting to the source. Yeah, first itself I have said. So let's write the set value method. Within that, let's mention the same thing. So I'll just go with static here. So this doesn't return anything. It will be void. I'll just go with the value. So this is fine. So let me go with the parameter I, j, as well as k, as well as k. Yeah. So let me go with the k. So this is fine. Within the set value method, the first thing I'll just go with k equals minus k. Yep. Let me do one thing. I'll just consider small k here, right? So this is fine. So this is fine. Let me write the simple if condition. Suppose if j equals 0, in that case what I'll do, so we'll check whether k is greater than 0. Suppose if k is greater than 0, then the value will be positive and we have to connect to the sink. If the value is positive, we have to connect to the sink. If the value is negative, then we have to connect from source. Suppose if the k is greater than 0, then the value will be positive and we have to connect to the sink. For connecting to the sink, I'll just write in this way. This one, I, t, as well as k. Yeah. For this one, again, one more step. I'll just go with a t, I, as well as 0. Yeah, this part. So we are done with this part. Next, I'll just go with the else. Yeah. So if the value is negative, then we have to connect from source. So I'll just go with answer equals answer plus k. So this is also fine. So this will be add of s comma I. Then I'll just go with a negative, as we are dealing with the negative values, right? So I have to go with a minus k. So this is fine. One more step. I'll just go with I, s, as well as the 0. Yep. This part is, we have completed this part actually. Next, let's move on with the next part. Else, what I'll be doing. So suppose if the k is greater than 0, again we'll be doing the same thing. So I'll just go with if k greater than 0. In that case, we have the positive value. Then we have to connect from the source. So I'll just go with add s, I, as well as the k, and I'll just go with add again here. So I'll just go with I, s, as well as 0. Yep. So this is fine. Yep. So else, if the value is negative, then we have to connect to the sink. For that, I'll just write it different in a different way. Answer equals answer plus k, and let me make use of the add here. So this one will be it minus k. This one. So we'll be going with the same thing, but we'll be adding the different parameters it as well as the minus k. I'll just go with add I t. So let me go with the minus k. So this is fine. And let me go with add t, I, 0. Yep. So this is fine. Let me come out of this one entirely. Now let's go with the shortest augmenting path, nothing but the SAP. So I'll just go with one more method here. So nothing but static int sap. So this is fine. Let me go with the two parameters. One is x and another one is low. Another one is low. Yep. So within this particular method, first thing, so we have to check whether we have reached sync. So this one will be in this way. So I'll just go with, suppose if x equals t, then all we have to do is we have to return the flow directly. Yep. So this is fine. Simple. Next, let's consider the resulting variable, and let me initialize this one with a 0. Then let's move on with a for loop here. So this one will be int I equals head of x. Yeah, I equals head of x. So this is fine. I not equal to 0, and I, let me assign this one to the next of this one. What do we call I? Yep. So this is also fine. Then we have to check for the valid edge. Valid edge in the sense, I'll just go with if capacity of I, if capacity of I, if it is greater than 0, and distance of x, actually distance of x. So if it is equivalent to distance of this one, 2 of I. So yeah, 2 of I plus 1. In that case, what we have to do, I'll just go with a variable name delta here. Let me assign this one to shortest, this one augmenting path, nothing but we have considered the variable name SAP, right? So I'll just go with, so I'll just call this one, that variable itself. Let me go with 2 of I, and we have to consider the minimum value. So I'll just go with a math.min of, so this one will be capacity of I, comma low. Yeah, capacity I, low. Then let's move on with the further steps. So I'll just go with the capacity of I equals capacity of I minus delta. So this is fine. The next step would be capacity of I. Yeah, capacity of I. Let me make use of the XOR here. Capacity of I XOR 1. Same thing. The same thing plus delta again. Yep, the final step. So let me go with the flow. Flow equals flow minus delta. Yep. And finally, result equals result plus delta as well. Yep. So this we are done almost. So let me write the simple if condition here. Suppose if the distance of S, so if it is greater than or equal to N, in that case, what we have to do, or even when the flow is equivalent to 0. So I'll just go with flow. If it is equivalent to 0, in that case, all we have to do is we have to return the result directly. Yep, so we are done with this part. Let me format the code and yeah, let me format the code so that the code looks good. Now, let me come out of this one entirely. But so let's move on with the further things. So let's go with a gap, this one optimization. We need this. So I'll just go with gap of this one, distance of X. Yeah, so this is fine. Distance of X. So I'll just this one, what do we call? Reduce this one. So I'll just go with a minus minus here. So first, so this is just for the gap optimization. So I'll just go with if gap of distance of X actually. So this one will be distance of X. If it is equal to 0, then distance of S equals N. Yeah, so this is also fine. I'll just go with the distance of X. Let me increment this one, distance of X plus plus and gap of, so this one will be distance of X again. So let me increment this one. Yeah, so the last one is nothing but we have to return the minimum, this one, what do we call, maximum closure, nothing but that will be stored in the resulting variable. I'll just return the result here. Let me return the result. So this is it for the coding part. Yep, so now we have to go for the input output part as well, or this one. Yeah, basically within the main method, I'm gonna write this one input output part, everything that's related to the input output part, printing the output, considering the input, those things. Yeah, so that one usually I take it from the Google. Let me do that. Just give me a second here. Main logic, we have already written the main logic. Yep. So let me do one thing. I'll just come here and let me paste this one over here. Right. So let me format the code once. So I'll just explain this one quickly. One second. So buffer data and the print writer, buffer data and the string tokenizer. So this is purely related to the input output part. Yep. So this is fine. Now P, Q, and K nothing but P is nothing but here whatever we have considered. This is nothing but the docs. Q is nothing but the people. We have already discussed this one. Let me tell this one again. P docs, Q people, as well as K is nothing but the penalty. Yep. So suppose if the person is friend and he's unsatisfied, in that case, penalty of G will be we have to pay penalty G, right? So that's what they have mentioned in the question. K is nothing but the penalty G here in this case. So we have successfully this one, what do we call, defined the source and sink here, right? So this is fine. Next, we have set the initial genders. So this one, where we have set the initial genders. So this one string tokenizer from here to this one for loop until this one. We have set the initial genders. Then suppose if we need to flip the cost, yeah. So here certain docs comes with a 1. In that case, if the person wants the doc to be flipped, in that case we have to go with the flipping cost. We have to pay the cost B of I, if you remember that part we have written here, right? So this one, suppose if you are flipping the cost, suppose, yeah, if flipping is required, then we have to handle the docs. For handling the docs, this one, this part we have written for loop. Yeah, so this is purely related to the input output people. Along with handling the people, so within the approach we had also discussed that along with handling the docs, actually we have to handle the people as well. For handling the people, see here, I less than or equal to Q, I less than or equal to P, nothing but docs, I less than or equal to Q, Q nothing but it's related to the people. We have to handle people as well. This is for handling the people until here, right? So if operation until here, right, you can just pause the video and have a look into it. So if this one operation, so this one is equivalent to 0, in that case dog, we are this one going with a dog to person here, right? Dog to person, this one, right? So we have already written the implies method. So I have mentioned the implies method here, and we are going with the set value. So this is also fine. So here, yeah, dog, we are implying this one to the person actually. Yep. So this is fine. Else person to dog actually. Else we are going with the person to dog. Yep. You can clearly see this one dog to person. This is person to dogs actually. Else we have to imply person to dog actually. So that's what we have done here. So this is fine. We are almost done. And at the end, gap is nothing but for the this one. What do we call? Optimization purpose. And within the while loop, what we have written, we have to calculate the max. This one, what do we call? uh, maximum flow, or the we have to calculate the maximum closure actually, that we are doing it within the main this one, what do we call, while we have already we have made use of the result. So let me make use of the result itself rather than the answer variable. So I'll just go with res here. So this is fine. Initially we have mentioned res, I believe, where we have this one, or we have considered this one itself, I believe. One second. One second. Oh, we have considered here answer itself. So we have made use of this one several times, I believe. Or else let me change this one to res. Yeah, sorry. One second. This is fine. That res variable, another variable we had made use of. Okay. So yeah, finally, what we are doing here, after calculating the maximum flow, we are just going with the out.println answer. We are just printing the solution here, and out.flush is nothing but after running the code, immediately we have to get the output. As we are making use of the this one input output package, and we are going with a buffer reader actually. So we are just making use of the flush here, right? So this is purely related to the input output part. Yep. So I can just go with either close or the flush. So we are done with this part. So let's do one thing. Let's try to run the code. I'm yeah, a little bit worried about the answer variable. Yep. Let's do one thing. Let's change this one to the resulting variable. It's res. This one. Sorry, res from this one. Ans answer variable itself. Yeah. So let me change this one to answer. This one as well. This one as well, and this one as well. Now this is fine. All the errors should be gone. Yeah. Yeah. We do not have any error. Anyways. So now, yep. Let me format the code once. So let's do one thing. Now let's run the code. So I'll just run the code. If everything goes well, we have to get the correct output. Let's see. Yeah. So it is asking for the input. So let me open the Chrome. Let me copy this input. All we have to get is we have to get the output too. So as I have shown you within the approach, by considering this particular input, you can just go with the second input actually. If you're doing the same thing, if you're following mine, so you can just go with the second input and try for this one. You have to get the output 16. Follow the same steps actually. Maximum profit you have to get is 16 here, right? So just check. So don't blindly follow. You can just check in the same way. You have to get the output 16. I insist you to try out with the second input. Yeah. So first let me copy this one and let's check so whether we get the correct output or not. We are getting the output 3, which is wrong. We have to get the output 2, right? So for the second one, let me rerun this one. Let me do one thing. I'll just open this. Let me copy this one and let me paste it over here. So we are getting the output 22. Oh, 3 and 22 we are getting. We have to get 2 and 16 actually. Somewhere something we have done wrong. Let's check the code. So what mistake I have done here is, so while I have copy pasted this entire thing, I will. So I completely forgot to change from max edges to max nodes actually. So this one head, so head, this one is completely different, right? One second. Yeah. Head as well as distance as well as the gap, we have to go with the max nodes, right? Of size max node. That depends on the max node, not max edges actually. I'll just go with max nodes. This one. Yeah. Let me copy the same thing here. Let me paste it over here. Let me paste it over here. One more thing. So we are going with a XOR, right? So XOR operations actually. So instead of the -1, I'll just go with a 1 here. And one more thing, let's do one thing. Let's initialize the head with -1 initially. Yeah, we are initializing with -1 itself, right? So not the this one distance. We'll initialize the head actually. Head. I'll just go with a -1. Yep. So this is fine, I believe. This is it for the coding part. Equals 1. Now we have fixed these four things actually. So one more thing. I'll just go with a shortest augmenting path of this one method. So I'll just come here to this part. So here, have within the for loop, see, loop has to check -1 instead of 0 here. We are going with I not equal to 0. We are checking for 0 actually. We have to check for -1 actually. This is one mistake that I have done. So these are some of the mistakes basically. Max nodes I had completely forgotten. Top we have to go with a 1 rather than the -1. Because we are performing the XOR operations. XOR operations will break if we give -1. Yeah, I had checked that same actually. I just wanted to tell the same. So if you give -1, the XOR operations will break. So for the correct computation, we have to go with we have to consider top equals 1. Yeah, that we have to do. And here, instead of checking for the 0, we have to check for -1. I not equal to -1. Yeah, so this is fine. So we are done with this part. Let's do one thing. Let me run the code. Yeah, let me run the code. So I'll just come here. Let me open the Chrome. Yep. So I'll just copy this one and let me paste it over here. So yeah, now we are getting the output 2, which is absolutely correct. Let me rerun the code. Let's check for the second input as well. I'll just come to this part. So let me copy this one. We have to get the output 16, right? So I'll just open this one. Yeah. Why this is showing like this? Let me paste this one over here. So we are getting the output 16, which is absolutely correct actually. Yep. So we are getting the output 16, which is absolutely correct. So let me do one thing. As we are getting the correct output for both the inputs, so let me copy the entire thing here. One second. Just give me a second here. What happened to this one? Yeah. Let's continue with the same. I'll just copy this one entirely. So let me open the Chrome. Yep. So I'll just come to this part. Let me hit the submit button here. So yeah, I'll just choose the problem. One second. We are going with the problem E, the last one actually. Let me paste it over. Yeah, one chain that is required. So this one, it's completely related to the IntelliJ. We don't need this one. Apart from that, I don't have to change this one as this is Codeforces, I believe. Let's go with the same thing. Let me do one thing. One second. Yeah, let me hit the submit button. Let's wait for some time. I hope this works, man. Hmm, we have debugged this one correctly. Yeah, running on test 2. Let's see. Let's wait for some time. It'll take some time. Yep. Let's wait for some time. Yeah, you can clearly see here the verdict that we got here is accepted. So whatever the code that we have written works absolutely correct for all the test cases, right? So one second. Why this is not getting open? Yeah, you can clearly see here. The verdict that we got here is accepted. So this is fine. Now we are done with solving the problem. This one, biologist actually. Yep. So we are left with only one thing that we have to discuss the complexities for the code that we have written for this particular one itself, right? So let's do one thing. Let's quickly discuss the complexities for the code that we have written. Let's do this one very quickly. So what will be the time complexity actually? One second. Just give me a second here. Did I miss anything? No. Yes. Let's do one thing. I'll just go with, yeah. So what will be the time complexity here? The time complexity. Oh, why this is not? 1 second. So yeah, I'll do one thing. So let me select this one. So yeah, what will be the time complexity actually accordingly with the code that we have written? The time complexity would lead to big O of e into square root of v. So we have went with a shortest augmenting path optimized flow. As we have went with the this one shortest augmenting path flow. So this one it varies. It is not exactly as theoretically that it has to be as we had considered for the algorithm actually. Rather, it would be e into square root of v. Yeah, e into square root of v, or we can, yeah, I can just write it on this way. It's e into square root of v. Yep. So this is fine, I believe. So we can just consider this is almost equivalent to, I have already shown you this one. This is almost equivalent to big of edges into the nodes actually. Big of number of edges into nodes. We had considered in the algorithm v into e, right? So v is nothing but n. Vertex and nodes are same, right? So v is nothing but n. Here it is almost equivalent to v into n or e into n. So v into e or this one e into n, both are same actually accordingly with the algo, right? So this is it for the time complexity part. So what will be the space complexity here? Space complexity would lead to, 1 second, space complexity would lead to big O of v plus e. You would have already guessed this one. Accordingly with the algo, it completely, the memory completely depends on the vertex as well as the edges. Yeah. So the overall space complexity would lead to big of v plus e itself. So the time complexity and the space complexity for the code that we have written would lead to big of e into square root of v and big of v plus e respectively. So this is it for the this one complexities part, and this is it for the this particular problem as well. We have successfully solved the biologist problem by making use of the this one, by implementing the maximum closure of a graph. And let me tell you one thing that we are done with the advanced graph algorithms. We have successfully discussed 10 advanced algorithms. So let me read this one out loud. What are the algorithms that we have this one actually discussed? So the first algorithm was Gomari-Hood tree, so which is very important. Second one was Stoya-Wagner global minimum cut, which is very important as well. Then we went with Shauliu Edmonds directed MST. Then we went with Blossom algorithm. Next, fifth algorithm, we went with this one, minimum mean cycle or the CARP algorithm. Sixth one, we went with a Howard minimum cycle min. Seventh one, we went with this one, Stoya Wagner, this one, Stoya, not the Stoya Wagner. Instead, we went with the this one. What do we call? Uh, Steiner forest algorithm. Yeah. So the eighth one we went with previously we went with two algorithms, matroid intersection as well as the matroid union. Eighth one as well as the ninth one. Yeah. So the final one, 10th one, just now we discussed the minimum closure of a graph algorithm and we implemented the same within the all within this particular problem. Yeah, we got the AC here. Now we are done with the problem actually. Now we are done with the problem. So we are left with only this one. Yeah, we are done with the advanced this one, advanced graph based algorithms playlist. From tomorrow we'll be starting this one, dynamic graph algorithms playlist. Yeah, so we'll be starting dynamic dynamic graph based algorithms playlist, so which consists of mainly the first one, fully dynamic connectivity, or it is also called as this one, mm, Hornday, this one, Lichtenberg algorithm, I believe. Yeah, Lichtenberg Thorup algorithm. So that one we will be discussing. First one. The second one will be going with the dynamic minimum spanning tree or dynamic MST. Third one will be going with the dynamic transitive closure, which is very important. Fourth one, offline dynamic connectivity, as well as fifth one will be DSU with the rollback. Usually, offline dynamic connectivity and the DSU with the rollback. Usually, we get to implement those two things in a single problem many a times, right? Offline, this one, dynamic connectivity as well as DSU with the rollback. We have implemented the DSU with the rollback very recently, twice or thrice actually. Not twice or thrice, at least once we have implemented. I do remember within certain problem we had implemented the DSU with a rollback. At least once we have implemented. Yeah. So this is fine. It will be easy as we have already implemented. So if you know the DSU algorithm, DSU with a this one rollback will be a piece of cake actually. It will not take much time. Yeah. So this is fine. That is the reason I say that you have to know certain this one basic algorithms. Yeah, basic algorithms in the sense BFS, DFS, those algorithms. This one Dijkstra's, Bellman-Ford algorithm, Johnson's algorithm, Floyd-Warshall algorithm, and this one Prim's for the MST actually Prim's algorithm as well as the Kruskal's algorithm. This one Kosaraju's algorithm, topological sorting. Yeah, these kind of algorithms we have already discussed actually. Yeah, within the 150 algorithms playlist and the graph-based algorithms we had already discussed the basic algorithms. 20 or 21 algorithms we had discussed if I remember correctly. Yeah, you can just check that particular playlist. If you don't know the BFS, DFS, topological sorting, DSU, yeah, and certain this one Kruskal's Prim's algorithm, these kind of algorithms, if you don't know, while solving the problem or while implementing this one, while discussing the complex algorithms, those algorithms might use the basic algorithms, right? So you'll not understand anything, right? I insist you to go through that particular algorithm, even if you have directly hopped into the advanced algorithm itself. So even if you're learning, so you can just go through that algorithm and you can just come back and you can just continue with the same actually. That I insist you to do that, or else you'll not get to know anything. You have to blindly implement certain things, which will not be good actually. Yep. So this is fine. This is what we'll be doing next. We are done with advanced graph-based algorithms. Next, as I've said, we'll be discussing dynamic graph-based algorithms. Yep. So there are 5 algorithms, dynamic graph-based algorithms. I mentioned the same actually. Yeah. Just now I mentioned the same. Those 5 algorithms we'll be discussing. Yep. So I hope this algorithm, maximum closure of a graph actually, this particular algorithm is completely clear, right? And we have got the opportunity to implement. This is one of the best problems to implement the maximum closure of a graph algorithm. Yep. So we have got an opportunity to implement this particular algorithm within this problem. So yeah, I hope the algorithm is completely clear. For now, this is it. Thanks for watching, guys.